Welcome to the optional bonus video about proving Theorem 39. So there are a couple of reasons why you might choose to skip this video, and then that's fine. One is that in order to effectively use ordered pairs, you don't really need the ideas in the proof of this theorem. You mainly need the theorem itself. You need the statement. So you need to know how to use this theorem, but the ideas in the proof are not necessarily going to help you more effectively work with ordered pairs. Another reason you might want to skip this video is if you feel like you benefit more from just reading on your own the proof rather than reading and seeing a video or just seeing a video. A couple of reasons to watch this video. One is that it's good practice to see kind of just another chance to practice something, right? More practice is better, to see the thought process involved in writing proofs. And another reason you might want to watch is because you're going to be using this fact a lot, and you might feel a little bit guilty about using it without seeing why it's true. So if you have that kind of conscientiousness, which is definitely a good personality trait to have for a good mathematician, then that might be a reason to look at how we would prove this, or just read it. Okay, anyway, if you're still here, so let's look at the proof together. So there'll be two directions. From left to right, I'll prove that if two pairs are equal, then the first positions and the second positions match up. And from right to left, if the first and second positions match up, then the pairs are equal. Let's do the easy one first. I like to get the easy one out of the way so I can end my experience with the more interesting hard one. Okay, so here's the easy direction. Assume x equals u and y equals v. Then what? So how do I prove that these two things are equal? Well, remember how to use equality used. If two things are equal, then any statement you can make about one thing is going to be equivalent to any statement you can make about another thing. Okay, that's for statements. So that's axiom 2, what I'm describing there. Similarly, there's something for terms. I think it was theorem 4. Let me scroll up here. There's something for terms. So in theorem 4, remember this temporary notation, the smiley face, stood for any old term you could write down. So if you take any old term, and so assuming that two things are equal, like x equals y, then you can take any old term, and if that term involves, maybe this is an easier one to read, take any old term and then replace all the x's by y's, and then those two terms will be equal. Yeah, so the easiest one to use probably is theorem 4, part 4. So then by theorem 4.4, let's call it, xy equals uv. So I've actually used it twice. I've used theorem 4.4 twice. I've used it once to replace the x by something it's equal to, which is u, and then again to replace the y by something it's equal to, which is v. So I'm not getting into so much detail about this, but if I really want to expand out the details, then here's what I'm doing with theorem 4.4. I'm applying it to, first, smiley face is going to be this. This is my smiley face. And then smiley face with x replaced by something it's equal to is this. And theorem 4.4, is that what it was? 4.4 tells me that these two are equal. And then I'll apply theorem 4.4 again, but to this situation where now this one is the smiley face, and then the two equal things that lead to a replacement is y is getting replaced by v. So we end up there. So one application of theorem 4.4 gives me this equality between these two. Another application of theorem 4.4 gives me this equality, and then transitivity of equality gets me from the beginning to the end. Okay, so those are kind of details that I'm leaving out, and generally it's always okay to leave out the details of how you're using axiom 2 or how you're using theorem 4 or even theorem 3. Those are sort of basics about equality that it would just take us, it would make our proof so long if we wrote those things out in so much detail. Okay, so that's it for that direction. That was the easy one. Let's do the hard one. I mean, this is nothing, right? This would have been true about doubletons also. If x equals u and y equals v, then doubleton xy equals doubleton uv. Nothing special there. This is the special direction. So now assume that this pair equals this pair. Now, how do I proceed from here? I cannot do anything without using the definition of ordered pair, right? I have to use the definition of ordered pair. So let me go back here, go find the definition. Here it is. It's this funky thing. Let me just write that so I can stare at it, so I can have it in front of me and stare at it. So then, I think I'm going to need more space. Then this doubleton, which consists of a singleton and a doubleton, is equal to this one. Okay, so I'm in a situation where I have two equal doubletons. Now, what does that tell me about the things inside the doubletons? Can I just go and say that, therefore, this equals this? No, it doesn't work that way. But maybe I can do something fancy, like observe that singleton x is in there. Singleton x is in this doubleton, thanks to the fact that singleton x equals singleton x, and so singleton x equals singleton x, or singleton x equals doubleton xy. Okay, then after arguing for that, then I can say, therefore, since these are equal, singleton x is in there. So that means singleton x is one of these two. Okay, but this is all probably sounding familiar. It sounds like something we've done before, right? Something we've done before. Where did this happen? Back here in theorem 23, when we proved that when two doubletons are equal, blah, 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 a bunch of stuff happens. So we already have a utility here, a theorem that helps us with drawing conclusions from having an equality between two doubletons. So why not recycle the work? Let this do make our life easier here rather than redoing the work. So now we can conclude by theorem 23, since we have two equal doubletons, we can conclude that either the first positions and the second positions match, or the inners and outers match. By theorem, I already forgot the number, 23, by theorem 23, either the firsts match and the seconds match, or it's like this instead. Okay, so I have an or now. That means I am going to get a case split. Remember my goal. My goal is to prove that x equals u and y equals v. And what I now know is that either we have this or we have this. So if I can prove my goal, if I can prove that either way, in either case, x equals u and y equals v, then I'll be good. Okay, so I hope you see why my brain went immediately to case split. It's because I have an or. When you have an or, the way to use that is a proof by cases. It's one way to use that. Okay, so case 1. And then I can use the power of copying and pasting. Suppose this junk. And I can even resize it. And there I've copied the other one. That's case 2. Suppose the other one. Okay, so let's fill out each case, and hopefully in each case we can make an argument for the goal, which is this: x equals u and y equals v. Alright, so here I have two things to work with: the equality of these singletons and the equality of these doubletons. This one looks familiar, so I could try to do some fancy stuff using the definition of singleton to work with this. And if I had no tools in my tool belt, then that's what I would do. That's what I'd have to do, right? I have to use the definition of singleton to work with this. Just like here, where we have this equality of ordered pairs, I have to use the definition of ordered pair to work with it until I have tools. But for singletons, I do have tools. So, oh, it's right here already. Theorem 21. Two singletons are equal if and only if the occupant, the thing inside the singletons, are equal. So, by theorem 21, x equals u. Ah, that's good progress, right? X equals u. So we already got one of the two things we want to prove. Okay, and now I've got this equality of doubletons. Okay, here we go again with theorem 23. Again, if I didn't have tools like theorem 23, then in order to do anything here, I would need to use the definition of doubleton. And this whole proof would just be really long, because it would probably contain inside it a proof of theorem 23. But luckily, I do have this tool, theorem 23. So by theorem 23, either x equals u and y equals v, or x equals v and y equals u. Okay, so that's another or. So it looks like I get another split into cases. So let me just accept the case split. It's okay. These are just another case inside this case. Nothing wrong with that. Maybe there's a more efficient way to do this, but it's not a huge deal. Let's just see what happens in the individual cases. So let's call this case 1.1, and the indentation helps here, but it's not necessarily standard. People don't always indent like this, but the numbering, if you don't indent, then the numbering will tell you how things are getting organized. Okay, so suppose x equals u, in case 1.2, suppose, oh, I'm sorry, this should be suppose x equals u and y equals v, right? Case 1.2, suppose x equals v and y equals u. Okay, great. So, can I get victory in all cases? My goal was to prove x equals u and y equals v, actually, right? So here we are done already, right? Then we are done. Great, that's it for case 1.1. Case closed, because this heading here tells you what we're trying to do, right? This tells the reader we're trying to prove from left to right, so we're trying to assume this and show that this follows. That means when we reach this in a case closed, that's done. All right, how about here? X equals v and y equals u. Now, I already have x equals u, and my goal is to prove that y equals v, right? I have x equals u, and my remaining goal is to prove that y equals v. So here in this case, where x equals v and y equals u, how do I prove y equals v? Well, my only hope to prove y equals v is to prove that u equals v, right? But remember, we are still in case 1, where we have x equals u. So if x equals u and x equals v, then u and v must be the same. So here case 1.2 is one of these cases where things are collapsing. Everything is x, y, u, and v end up just being the same. So let's remind the reader about x equals u, since that was a couple of sentences ago, they may have forgotten. Since x equals u, we have u equals v. This is by transitivity by theorem 3, but we don't need to reference something like that. Okay, so notice when I'm writing this, I could have just said, then we have u equals v, but that's kind of mean. It's good to remind why. Since x equals u, here's x equals v, so u equals v. Thus, here we have y is u is v, y is v, that's what I want to end with. And that is victory. I recently mentioned x equals u, and here's y equals v. So we are done. Yay. So these two cases are closed. Now for case 2. So case 1 is closed also, right? Once you close all the subcases inside it, case 1 is done. So case 2. This is an interesting one. Here's one where we have singletons ending up being equal to doubletons. Now, if you want to, if you're finding this enjoyable, I think it's pretty fun. If you want to, this might be a good time to pause and then just try to work it out on scratch paper. See if you can finish case 2. And now I'm going to assume that you have unpaused or that you're just watching continuously, and we can proceed. So we actually have a tool for working with singleton equals doubleton. So we don't need to go all the way back to using the definition of singleton and doubleton. We have this tool that says a doubleton equals a singleton if and only if everything in sight is just all equal. Everything inside is all equal. So in case 2, we have by, what was it, theorem 22. By theorem 22, we have x equals u equals v, right? All of these are equal. And here, x equals y equals u. Okay, what was my goal? Was to prove x equals u and y equals v. So here's x equals u. Here's y equals u, but u equals v, right? So let's just put the pieces together. We're basically done. So we have x equals u, and we have, instead of just writing y equals v, let me write it kind of in a centered display here, where I create a chain of equalities from y to v, where each intermediate equality is one that I've already written down. This is a u, by the way. So we already have y equals u, and we already have u equals v. So that's how I'll end. X equals u and y equals v. And there we have it. That's it for case 2. That's it for the second direction here. And that is our essence of pairs theorem. So starting from now, you can forget about definition 38. You can totally forget about this and just feel comfortable knowing that this definition has achieved this property, that for this notation, that two pairs match up if and only if the corresponding positions match up.